Most of us, though, use mirrors for personal grooming every day. However, not many of us know how we are able to see a likeness of ourselves in mirrors. The images that you see on a polished surface can be explained with the phenomenon of the reflection of light. Light from your body and other objects reflects from shiny surfaces, like mirrors, to form an image of those objects on your eye lens. At the end of this lesson, you will be able to define reflection as a property of light, define terms related to reflection, incident ray, reflected ray and normal, state the laws of reflection, define images, identify the characteristics of images formed by a plane mirror, convex mirror and concave mirror. Apply the mirror formula and sign convention to find out the relationship between distance of object and image from a mirror. When a ball is thrown at any surface, it bounces back. Similarly, when light rays are incident on a surface, they bounce back. The bouncing back of light rays thus is known as the reflection of light. Based on the nature of the reflecting surface, there are two types of reflections: regular reflection and irregular reflection. Regular reflection is caused by a smooth surface where all the light incident on the surface is reflected in a definite direction. Regular reflection is caused by plane mirrors, still water and other smooth surfaces. Irregular reflection, also known as diffused reflection, is caused by irregular surface of the objects. The irregularity in the surface makes the incident light bounce back in different directions. Wood, wall, and other such irregular surfaces cause irregular reflection. Let us examine the phenomenon of reflection and the terms related with it. An incident ray is a ray of light incident on an object or a reflecting surface. A reflected ray is a ray of light that bounces back from a reflecting surface. The point of incidence is the point of an object or a reflecting surface at which a light ray is incident. Normal is an imaginary line drawn at the point of incidence, perpendicular to the reflecting surface. The angle of incidence is the angle between the incident ray and the normal, and is denoted by I. The angle of reflection is the angle between the normal and the reflected ray, and is denoted by R. Let us examine the properties of reflected rays by conducting an experiment. To begin, you need to fix a sheet of white paper on a drawing board. Draw a line MM' on it and mark a point O at the center of the line. Draw a normal ON on MM'. Next, draw IO, the incident ray, in such a way that angle IOM is less than 90 degrees. Place a strip of plane mirror vertically on MM'. Then fix two pins P and Q on the incident ray IO. P' and Q', which are the images of P and Q respectively, are observed from the other side of the normal. Two pins P1 and Q1 are fixed such that these two pins and P' and Q' are collinear. Remove the pins and draw a line OR passing through P1 and Q1 to represent the reflected ray. Now, if you measure the angle of incidence ION and the angle of reflection NOR, you will find that angle I is equal to angle R, and P, Q, P1, Q1, N, and O lie in the same plane. In other words, the experiment shows that the angle of incidence I equals the angle of reflection R. The incident ray, the reflected ray, and the normal all lie in the same plane. The property of reflection can be explained using mirrors. The laws of reflection affect our daily lives in many ways. In fact, we verify these laws every time we look into a mirror. which is a surface capable of reflecting sufficient undiffused light to form a likeness of an object placed in front of it. The likeness showed by a mirror is called an image. There are two types of images. Real images are the images that can be caught on screen. For example, the images projected on a screen or images taken using a camera are real images. Virtual images are the images that cannot be caught on a screen. Images formed in a plane mirror are virtual, as they disappear when the object is removed. Mirrors can be broadly classified into plane mirrors, which have flat surfaces, and spherical mirrors, which have curved surfaces. In this lesson, we will look at reflections in plane mirrors. Plane mirrors have flat, smooth surfaces. Plane mirrors are most commonly used for personal grooming, decoration, and architecture. These mirrors are constructed by coating silver on one side so that the other side can reflect smoothly. To see how an image is formed in a plane mirror, let us do an experiment. Consider an object in the shape of the letter P. From a point X on the object, consider a light ray incident on the mirror at point A. According to the law of reflection, the angle of incidence is always equal to the angle of reflection. Observe the angle of the incident ray as it reflects and travels to the eye. From the same point X on the object, another light ray is incident on the mirror at point B, and the reflected ray travels to the eye. The two reflected rays from A and B are divergent. When extended beyond the mirror, these rays meet at X dash. Thus, the image of the point X on the object is formed at X dash. Consider one more point Y on the object. A light ray from Y on the object is incident on the mirror at C, and the reflected ray travels to the eye. Similarly, another ray from Y on the object is incident on the mirror at D, and is reflected to travel to the eye. Like the two rays from A and B, the two reflected rays from C and D are divergent, and when extended beyond the mirror, meet at Y dash. Thus, Y dash is the image of point Y on the object. Similarly, rays from all points on the object are incident on the mirror. All these divergent rays are extended beyond the mirror to form the complete image of the object. You will also notice that the image formed in this case is erect, laterally inverted, of the same size as that of the object, and the distance of the image from the mirror is equal to the distance of the object from the mirror. These are standard characteristics of images of objects formed in plane mirrors. How will you verify whether the distance of the object from the mirror actually equals the distance of the image from the mirror? Consider two rays from a point object O placed in front of a plane mirror. The ray of light, which incidents normally at point A, is reflected back along the same path. However, the second ray, which incidents at point B, is reflected along BC. This ray obeys the law of reflection such that N is the normal as shown. The reflected rays AO and BC, being divergent when extended beyond the mirror, meet at O dash to form the image. In triangles OAB and O dash AB, angles OAB and O dash AB are equal to 90 degrees. Also, based on the law of reflection, angle I is equal to angle R. Angles on alternate sides of the transversal on two parallel lines are called alternate angles and are always equal. Here, angle I and BOA are alternate angles. Therefore, angle I equals angle BOA. Angles in similar locations with respect to a transversal on two parallel lines are called corresponding angles and are always equal. Here, angle NBC and angle BO-A are corresponding angles. Therefore, angle R is equal to angle BO-A. Therefore, angle BOA is equal to angle BO-A. Using the angle, and side property of equal triangles, we can say that triangles OAB and O-AB are equal. Equal triangles have equal sides. Therefore, OA is equal to AO', which means that the distance of the image from the mirror is equal to the distance of the object from the mirror. Let us switch to another aspect of images in mirrors, the relationship between the mirror and the image size. You may have noticed that not all mirrors enable you to see your full image. You typically need a tall mirror to view your full image when getting ready to go somewhere. This is why most bedrooms sport tall mirrors called full-length mirrors. Clearly, image formation is affected by the size of the mirror. A simple experiment can help you determine how tall a mirror you require to view your full image. Consider a person of height HF standing in front of a mirror on the wall, where H represents the highest point on his head, F the lowest point on his feet, and the eye E at eye level. The person will be able to see his full image if he can see points A and B. The mirror requires a height where the incident rays HM and FM, after reflection, reach the eye of the person. These will form an image H', F' when produced backwards. In triangle HEH', AM is parallel to HE, and A is the midpoint of HH'. Therefore, M is the midpoint of H'E. Similarly, in triangle FEF', NB is parallel to FE, and B is the midpoint of FF'. Therefore, N is the midpoint of F'E. Now in triangle H', F'E, M is the midpoint of H'E, and N is the midpoint of F'E. Therefore, MN is parallel to and half of H', but H', is equal to HF. Therefore, MN is equal to half of HF. Thus, in order to see his full-length image, a person requires a plane mirror that is half his own height. Therefore, to view the complete image of an object, you need a mirror that is at least half the height of the object. Kids sometimes use mirrors as playthings, where they rotate the mirror in the sunlight to make the sun's rays reflect on another person or an object. Suppose a child uses a mirror to direct the sun's rays to a friend standing at a window on the first floor. Now he wants to direct these rays to another friend standing on the road some distance away. If the lines joining the boy to the two friends make an angle of 120 degrees, by what angle should the child rotate the mirror? To solve this problem, let us see what happens to a reflected ray when a mirror is rotated through an angle. Consider a ray of light IO incident on a plane mirror in position M1, M2, such that OR is the reflected ray and ON is the normal. Therefore, based on the laws of reflection, angle RON is equal to angle ION, which is the angle of incidence I. Therefore, angle IOR is equal to twice the angle of incidence. Let the mirror be rotated through an angle theta about point O, so that M1', M2' is the new position of the mirror, and ON' is the new position of the normal. the position of the incident ray remains the same. But the new angle of incidence is angle ION dash. Angle ION dash equals I plus theta. Let OR dash be the reflected ray such that angle N dash OR dash is the new angle of reflection. From the figure, you can see that angle IOR dash is equal to angle ION dash plus angle N dash OR dash. Substituting ION dash and N dash OR dash in terms of I and theta, you get angle IOR dash is equal to 2I plus 2 theta. Subtracting equation 1 from equation 2, we get angle IOR dash minus angle IOR is equal to 2I plus 2 theta minus 2I. Therefore, angle ROR dash is equal to 2 theta. Thus, for a given incident ray, if the plane mirror is rotated through a certain angle, then the reflected ray rotates through twice that angle. Hence, for the given problem, if the child has to direct the rays to a person standing 120 degrees apart, he has to rotate the mirror through an angle that is equal to half of 120 degrees, that is 60 degrees. Have you ever wondered about how images are formed in a kaleidoscope? A kaleidoscope uses 3 mirrors placed at an angle to produce multiple images. When mirrors are placed at an angle, the reflected ray from the first mirror is incident on the second mirror. The second mirror in turn reflects it back to mirror 3. Thus, multiple images of the object are formed. The number of images seen in such an arrangement can be calculated using the formula n is equal to 360 divided by theta minus 1. Based on this formula, if the angle between the mirrors, theta, is 90 degrees, then the number of images formed is 3. Experimenting further, if 2 parallel mirrors are placed with their reflecting surfaces facing each other, the mirrors form an infinite number of images between them. This is because the angle between the mirrors placed in this manner is 0. Mirrors can be placed at angles to change the direction of light received by the eye. For example, 2 mirrors placed at specific angles are used to make optical instruments like periscope. Periscope is used in land and sea warfare, submarine navigation, and elsewhere to enable observers to view their surroundings while remaining under cover, behind armor or submerged. A reflecting periscope consists of 2 mirrors to change the direction of light coming from the scene observed. The first mirror deflects the light down through a vertical tube. At the bottom of the tube, another mirror is placed at an angle to reflect the light towards the observer's eye. Most amusement parks have a hall of mirrors, a traditional attraction. Mirrors in these halls are often distorted into different curved, convex or concave shapes to give the participants unusual and confusing reflections of themselves. They may see stretched, shrunken, or even bloated forms of their images. Sometimes the images are startling, and at other times hilariously funny. Thus, the hall of mirrors can use properties of spherical mirrors to create an unusually funny experience for visitors. Of course, that's not the only area where spherical mirrors are used. You may be using spherical mirrors in your everyday life without being aware of it. In this lesson, you will learn about types of spherical mirrors and their uses. At the end of this lesson, you will be able to describe spherical mirrors, identify the characteristics of images formed by a convex mirror and concave mirror, and apply the mirror formula and sign convention to find out the relationship between distance of object and image from a mirror. A spherical mirror is made from a part of a hollow sphere of glass. In other words, it is a plain glass bulging inwards or outwards. Spherical mirrors are further classified as convex and concave mirrors. A convex mirror reflects light from its outer spherical surface and has a silver coating on its inner surface. Convex mirrors are usually used as rear-view mirrors in automobiles. A concave mirror reflects light from its inner spherical surface and has a silver coating on its outer surface. Dentists usually use concave mirrors to examine teeth. You need to be familiar with the terminology used in calculations involving spherical mirrors before you get into more detail. Let's start with the center of curvature. Center of curvature, C, is the center of the sphere of which the mirror is a part. Radius of curvature, R, is the radius of the sphere of which the mirror is a part. Pole, P, is the geometric center of the spherical mirror. Aperture is the surface of the mirror used for reflection. Principal axis is the line joining the pole and the center of curvature. Principal focus, F, is a point on the principal axis. This is the point where the rays in the reflected beam, formed from the incident beam parallel to the principal axis, converge. Focal length, F, is the distance of the principal focus from the pole of the mirror. Objects seen in the mirror are closer than they appear. You may have seen this warning sticker on the rear-view mirrors in your cars and bikes. These rear-view mirrors are actually convex mirrors. Rear-view mirrors help the driver to keep an eye on a large area behind the vehicle by providing a wide field of view. The behavior of the light rays reflected from a convex mirror varies based on the angle of incidence on the mirror. Let's take a look at a few cases of reflection of a light ray from a convex mirror, taking the example of a rear-view mirror. In the first case, incident rays are parallel to the principal axis. In this situation, the reflected rays appear to pass through the focus. In a rear-view mirror, incident rays parallel to the principal axis enables the driver to see the car traveling exactly behind his car. In the second case, let us consider incident rays directed towards the center of curvature. Here, the angle of incidence is 0. Hence, the angle of reflection too is 0. Thus, the reflected rays retrace the path of the incident rays and appear to pass through the center of curvature. This enables the driver to see the parking meter on the other side of the road. Next, look at incident rays that are directed towards the principal focus. The reflected rays go parallel to the principal axis. This is how the driver is able to see the traffic signal which the car has crossed. Finally, if incident rays strike the pole at an angle with the principal axis, the reflected rays also make the same angle with the principal axis. This helps the drivers of two cars traveling alongside to look at each other in the rear-view mirror of the car ahead. In concave mirrors, such as a dentist's reflector, the reflection of rays is somewhat different from that in convex mirrors. Concave mirrors help enlarge the images of faraway objects or view objects that you cannot directly see due to their position. As in convex mirrors, reflection of rays in concave mirrors also follows certain rules. If the incident ray is parallel to the principal axis, the reflected ray passes through the focus. If the incident ray passes through the center of curvature, the reflected ray retraces the path of the incident ray. If the incident ray passes through the principal focus, the reflected ray goes parallel to the principal axis. If the incident ray strikes the pole at an angle with the principal axis, the reflected ray also makes the same angle. The focal length of a spherical mirror depends on its radius of curvature. Consider a ray Q parallel to the principal axis incident at point M on the mirror. This incident ray is reflected in accordance with the laws of reflection. When the reflected ray is extended beyond the mirror, it meets the principal axis at point F, which is the principal focus of the mirror. We know that angle I is equal to angle R by the laws of reflection. Angle I is also equal to angle MCF, as they are corresponding angles. Additionally, angle R is equal to angle CMF, as they are vertically opposite angles. Therefore, angle MCF is equal to angle CMF. Therefore, CF is equal to MF. If point M is very close to point P, that is, the linear aperture of the mirrors is very small, then MF is equal to PF. Therefore, CF is equal to PF. Also, PC is equal to PF plus CF. Or, PC is equal to 2PF, since CF is equal to PF. Therefore, R, the radius of curvature of the spherical mirror, is equal to 2PF. But PF is nothing but the focal length of the mirror. Therefore, R is equal to 2F, or F is equal to R divided by 2. Hence, in case of spherical mirrors, the focal length is half the radius of the curvature. When a beam parallel to the principal axis is incident on a convex mirror, its rays diverge. These rays, when produced backwards, appear to diverge from a point known as the principal focus. The image formed by a convex mirror is always erect, virtual, and diminished in size. The location of the object does not affect the characteristics of the image. Thus, as the object approaches the mirror, the image approaches the mirror too, but not proportionately. This is why the rear view mirrors of cars and bikes are made of convex mirrors. When a beam of rays parallel to the principal axis is incident on the reflecting surface of a concave mirror, its rays all converge at a point on the principal axis. This point is known as the principal focus of concave mirror. Unlike a convex mirror, the nature and size of the image in a concave mirror depends on the relative position of the object from the mirror. Let us examine the characteristics of the image of an object at different points in front of the mirror. When the object is at an infinite distance, the image is formed at the principal focus F. This image is real, inverted, and highly diminished in size. When the object is placed at a finite distance greater than the radius of curvature R, the image is formed between the principal focus F and center of curvature C. This image is real, inverted, and diminished in size. When the object is placed at center of curvature C, the image is formed at the same point, that is, at C. This image is real, inverted, and equal in size to that of the object. When the object is placed between the principal focus F and the center of curvature C, the image is formed beyond the center of curvature C. The image in this case is real, inverted, and magnified. When the object is placed at the principal focus F, the image is formed at infinity. This image is real, inverted, and highly magnified. When the object is placed between the principal focus F and the pole P, the image is formed on the side of the mirror that is opposite to the object. The nature of this image is virtual, erect, and magnified. Now, based on your knowledge of spherical mirrors, let's examine how these mirrors are used in amusement parks. The hall of mirrors that you saw earlier uses combinations of concave and convex mirrors to show funny, distorted images to the viewer. Concave mirrors are converging mirrors. They help us view enlarged images. Therefore, if you stand close to such a mirror, you will see a wider, fatter image of yourself. On the other hand, standing close to a convex mirror would make you appear thinner. With the set of such mirrors around you, you can see a variety of images of yourself, an undoubtedly interesting experience. The analysis of properties of images formed in convex and concave mirrors showed us that these mirrors present images that are either smaller or larger than the relevant objects. The ratio of the height of the image in a spherical mirror to the height of the object is called linear magnification. Linear magnification is denoted by small letter m. You can determine the size of the image reflected in a spherical mirror by using linear magnification. You can also compute magnification as the ratio of image distance to object distance. Thus, the ratio of the height of the image to the height of the object is equal to the ratio of image distance to object distance. Magnification can be unity, greater than 1, or lesser than 1. Magnification is unity when the size of the image is equal to the size of the object. When you look at your image in a plane mirror, it is of the same size as yours. Therefore, the magnification of plane mirror is unity. In other words, there is no magnification. Magnification is greater than 1 when the size of the image is greater than the size of the object. When the object lies between C and F of a concave mirror, the image formed is inverted, real, and bigger in size compared to that of the object. In this case, the image is said to be magnified. Thus, magnification is greater than 1. If the object is placed between F and P of a concave mirror, then the image formed is virtual, erect, and bigger than that of the object. Hence, in this case also, the magnification is greater than 1. Dentists use this situation to view the inner parts of a mouth with more clarity. Magnification is lesser than 1 when the size of the image is lesser than the size of the object. When an object is placed beyond C of a concave mirror, the image formed lies between C and F of the mirror. It is inverted, real, and the size of the image is lesser than that of the object. Thus we say that the image is diminished and its magnification is lesser than 1. In the case of a convex mirror, irrespective of the position of the object, the image formed is virtual, erect, and its size is smaller than that of the object. Hence, in a convex mirror, the image formed is always diminished and its magnification is lesser than 1. Suppose an object is placed in front of a concave mirror. The distance between the object and the mirror is 30 centimeters. The focal length of the mirror is 10 centimeters. How will you find the position of the image? The object distance, image distance, and focal length in a spherical mirror are related. The mirror formula defines the relationship between these aspects. 1 divided by F is equal to 1 divided by U plus 1 divided by V, where focal length F is the distance between the pole P and the principal focus F. Object distance U is the distance of the object from the pole P of the mirror. Image distance V is the distance of the image from the pole P of the mirror. all distances are measured from the pole. The distances measured in the direction of the incident light are taken as positive. The distances measured in the direction opposite to that of the incident light are taken as negative. Try to apply the mirror formula in this problem. According to the problem, U is equal to 30, F is equal to 10. According to the mirror formula, 1 divided by F is equal to 1 divided by U plus 1 divided by V. Substituting the values for F and U in the formula, you get V is equal to minus 15.